Okay, continuing with our theme, but the last couple of presentations slightly veered away from the name of Gullstrand. So let me try and change the direction of the vehicle and pull us back towards Gullstrand and Gullstrand's legacy. One thing about Gullstrand's work, which earlier this morning we had a resume of his life and his contributions, there are certain things that Gullstrand completely ignored. And the one thing in his work that he completely ignored was the tear film. And as all of you know, even those of you wearing optical correction, whether using lenses or pharmacologically induced, if you blink and stare at the screen, within 15 or 20 seconds, your eyes are going to get uncomfortable. We all know that. Because the tear film has a finite stability. But Gullstrand completely ignored the tear film in his model eye. Funny thing is, Gullstrand, just like some of his other co-workers, no, let me rephrase that, other people working in the field, when they produced their model eyes, they assumed that the cornea was a single unit, uniform layer of tissue with one refractive index. If you look at the Shirley model eye, which was published in 1904, 5 years before Gullstrand's publication in 1909, if you look at the original Helmholtz work, which was done in, I believe, 1866, the refractive index of the cornea was regarded as uniform. And we know from work stretching back from 1863 to the current time, if you add water to a tissue, you will change its refractive index. And this slide on the right-hand side shows that as the water content of the bovine corneal stroma is increased, its refractive index goes down. And these yellow triangles are data actually taken from laboratory tissue. These two other lines are theoretical lines according to Uri Fat, a great person, and Lang et al. In the late 70s. So we know that the cornea itself is of non-uniform refractive index. So we think we can now improve on Gullstrand's original model because the lack of uniformity in the refractive index of the cornea, which Gullstrand did not know about, actually accounts for some of the changes we used to see in the early days of PRK, when, as some of you who've used PRK and are particularly familiar with it, you know that epithelial hyperplasia has a direct link-up with the shift in the refraction during the post-operative healing period. And our argument, this is when I say our, I'm talking about myself with John Marshall and others, our argument was that the epithelium of the human cornea has a refractive index much higher than the anterior and posterior layers of the stroma. And this epithelium's refractive index is actually similar to the refractive index of some of the most popular soft contact lenses available. If you look at products such as the contact lenses manufactured by CooperVision, contact lenses manufactured by other companies, they have a refractive index, not all of their lenses, but some of their products, similar to the refractive index of the epithelium. And so we can now show that this thin layer over the cornea is acting like a lens. And because it acts like a lens, it contributes to the overall refraction of the eye. Let's go a little bit further forward still. From the corneal stroma, from the cornea to the epithelium, let's go further forward into the tear film. The tear film, as we all know, is not a single layer of water. No. It is a lot more complex over this very, very thin region consisting of glanky protein, watery protein, and a lipid layer. But throughout this thin layer, the refractive index is not uniform. It shifts. The actual lipids of the tear film has a refractive index between 1.40 and 1.53. This was work done by John Tiffany, that some of you in the audience may recognize from work he did in the mid-80s. And I, with some students of mine several years ago, we actually showed that the refractive index of the tears, if you take minute samples from the lower tear meniscus, the actual refractive index of the tears has a direct correlation with its protein content, more specifically lactoferrin. And as you get older, the refractive index of the tears shifts very, very slowly, and slightly, but significantly. So the tear film does not have a uniform refractive index, and throughout life, and it depends on the amount of protein and the amount of lipid that's present in it. Now, if you accept that the tear film contains lipid, the next question would be, where does the lipid come from? And the lipid, not all, the majority of lipid in your tear film comes from your meibomian glands. Now, some of you have actually performed this experiment with me, but what I'd like you to do for now is squeeze your glands. Now, this is not a form of self-abuse. What I want you to do is look up and pinch your lower eyelid 2 or 3 times. Glance up and pinch your lower eyelid 2 or 3 times. And what you will find is your vision becomes a little bit misty. Has anybody noticed that? Yes? I see some heads nodding. The reason why your visions become a little bit misty is that you squeezed out meibomian oil. What it has done is increase the stability of your tear film, but that extra lipid, because of its refractive index being higher than the watery content, what it's done is made your vision a little bit misty, because it hasn't mixed properly yet. So just like putting butter on bread, once you spread it, it becomes nice and even. But before you spread it, it's a lump. And you're blinking to spread that over. So, what does this all mean? It means that the lipid layer actually creates a series of optical diffraction or interference patterns over the surface of the tear film that we can actually see. And this way we can visualize the lipid layer of the tear film and actually decide whether somebody's lipid is insufficient and needs enhancing. Now, when you squeeze those lipids out, your vision became a little bit misty. Why? Because as I said, it didn't mix very, very well. Once it's mixed, it's fine. What we do know is that eyes that are dry, eyes with poor lipid or poor tear secretions, tend to have a lot of aberrations. And this was a thesis that I actually examined a few years ago by Montes-Mico. And what he found is that dry eyes tend to have, the optical quality of the eye is not as good as non-dry eyes. And what was also found then is that after you blink, the optical quality of your eye changes with time. It's at a peak around about 6 or 7 seconds after you blink, and then it degenerates. So, when you squeeze the lipid out of your eyes, your vision becomes a little bit hazy. And if you stare at this picture long enough, you will soon realize what you thought was in the picture is not actually in the picture. Has anybody worked out what's in that picture yet? It's funny, the guy that's actually took the pharmacological drops so he can see better in the distance has worked out what is actually in this picture before anybody else. Just bear that in mind in thought. Now, to sum up, the refractive index of the tears is not uniform. If it doesn't mix very well, it will compromise the tear film and it will reduce the optical performance of the tear film. And this is demonstrated by this slide here, where because the water has a poor surface and it's poor mixing, it causes aberrations. What we wanted to know in this little study was by putting in artificial tear solutions, can we actually improve the overall optics of the eye? We know that we can improve ocular comfort using tear enhancers, but can we actually improve the optics of the eye? And we did this using systems, using a Hartmann-Shack aberrometer. This slide just summarizes the patient group and the instruments we used in this particular study and how we did this. We compared two things: the actual tear enhancer with squeezing in extra lipid into your tear film, as some of you did earlier on. And these are the summarizes the results. What we found is that when you squeeze your meibomian oil out of your glands, you made the optics of your eye worse. You increased aberrations such as coma, spherical aberration, and the fifth order. They all actually increased quite significantly when the pupil was large as opposed to when the pupil was small, when the oil was added. When patients had a tear enhancer instilled, spherical aberration of the eye is reduced. So what this was telling us is that 20 seconds after this intervention, either putting in tear enhancers or squeezing the glands, right, did alter the overall optics of the eye. Gullstrand didn't know about that. We could also now measure this change in optical performance of the eye, which Gullstrand did not have the technology to do. So, in conclusion, the oil is good for you, but only if it's been administered properly, not forced out. Artificial tear enhancers are good for you. They actually improve the optical performance of the eye. And this might be useful to know, especially in those patients that are persistently complaining of their vision not being right. After you perform surgery, whether it's on the cornea or whether it's an implant lens you put in, or even when they're wearing contact lenses, when patients persistently say, yes, but it's not right, you look at visual problems, and it may be not a visual problem that's at fault. It's a tear film problem that's causing their difficulties. So when patients are persistently unhappy, let's try and enhance their tear film, because we can improve the overall optics of that eye. If you look at some of the tear enhancers available, on the market. Some of these are now defunct, I know. A lot of them have a refractive index which is outside the range of the normal tears. Some of them have pHs which are outside the comfort zone of the arterial eye. So when we look at, when you start to use tear enhancers, and some patients say, when I've used those drops you gave me, it made things worse. It's because some of those tear enhancers are too or acidic or too basic, or their refractive indices are just plain